It's my great pleasure to introduce our friend Mark Wilson, who's a distinguished professor of philosophy in the Department of Philosophy at Pitt. He's also a fellow of the Center for Philosophy of Science and has given us many talks over the years. Recently, he has published two very influential books. The first one is Wandering Significance, published now a few years ago with OUP that made a splash. And more recently, maybe a couple or maybe already 3 years ago, right, 3 years ago, time passes, Physics Avoidance and Other Essays in Conceptual Strategy, also with OUP. And I believe Mark is working on another book, but maybe we'll hear a bit more about that, or maybe not. And Mark worked on a range of topics in philosophy of science, in the philosophy of applied mathematics, on topics bearing on how to understand modeling in science, physics by scales, and so on and so forth. But he also has done an enormous amount of work in the philosophy of language and how the philosophy of language intersects with the philosophy of science. And today it's a real great pleasure to hear from Mark. So Mark, the floor is yours. And we'll be back in about 50-55 minutes for the Q&A. Thanks.
Okay. I've actually written, or almost written, 2 books by accident because I wrote for a little series who didn't tell me about their word limit. And so I wrote twice as long as they allowed, so I wound up with 2 books. Anyway, sure, they will be coming up. Okay. Okay, can you all see my overheads?
We can.
Okay, so this talk, which I may not get through all of, but I'll just end in a whimper if I need to, is about the structure of theory, or what we call theory, and their component parts. And the basic moral that I want to draw is that we need finer discriminative tools in talking about theories than philosophers typically employ right now. And I'm going to apply this to a theme that comes up quite often in philosophy. I'll come back to it. The status of what's an approximation and what is part of the official or fundamental theory. And many philosophers appeal freely to this notion, but in real life cases, it's a lot harder to apply than these folks presume. Okay, and when we do this, you often miss some crucial detail that's actually important in unraveling the confusions of the discipline. Okay, and the particular example I'm going to talk about today is the topic of so-called Maxwellian optics, classical optics in Maxwell's mode. And again, you frequently find philosophers writing as if there's just a clear-cut theory there, and from which you can distinguish the fundamental from the approximate. Okay. Now, what the basic moral that we're going to draw today, and which can be greatly extended beyond what I'll be able to say here, is that body of doctrine is actually an arrangement of ingredients that are tied together with the notion of frequency, which in this context, a pure frequency, which means a wave that travels in a sine wave pattern like this. It's also called monochromatic light. That is light of a particular frequency, which and the visible range would be associated with a spectral color. Okay. Now, the events I'm going to talk about here all have to do with that ingredient that ties these pieces together, namely frequency, right? And that notion, which you're usually taught in elementary optics, is a very fundamental notion, is a lot trickier than you first presume, and has caused some rather momentous reappraisals in what's going on in optics. Okay, and I won't go through this, but a quick example of this appeal to optics as if it's a perfectly clear theory can be found in John Worrell's well-known structural realism. Now, in point of fact, philosophically, I'm sympathetic to a lot of Worrell's ambitions. I'm a scientific realist of some sort, but you cannot lean on the notion of same equation, their same fundamental equation in different theories in the way he actually does to pursue his argument. We have to have much more refined tools of evaluation than he's employed for his so-called structuralism. Okay, now I'm not going to spend a lot of time with Worrell here. In fact, I won't spend any more time with him, except to say that there's a lot of complexity involved here, because I think I can show this complexity more easily by looking at a rather considerably more refined debate that occurred a couple of years ago between Bob Batterman and Gordon Bellott, and where some of the major issues come across quite clearly. Okay, now Bellott summarizes Bob's position roughly, well, as follows. The most provocative claim of the book is that fundamental physical theories can be expected to be explanatorily inadequate, that there exist phenomena that can be understood only when the conceptual apparatus of a fundamental theory, like the actual examples, Maxwellian wave optics, is supplemented by concepts whose home is in a less fundamental theory. And here he's thinking of ray optics as they appear in Bob's book. Now, let me make one brief observation so you don't get confused. Bob does sort of emphasize rays. In this talk, I'm going to emphasize pulses and wave fronts, right? Now, these two notions are intimately linked. They can kind of be or interdefinable. But for the features I want to bring out, concentrating upon the role of a wavefront. That is, a wavefront is the moving front surface of a ray. Okay, and we're going to concentrate on that and its role. But everything Batterman says can be translated into these terms. Okay, and here's the major response that Gordon made. But an examination of the sense in which rays and caustics are implicit in the apparatus of wave theory saps all intuitive force from Batterman's claim that here we have cases where the understanding of phenomena requires the resources of the more fundamental theories to be supplemented by the resources of the less fundamental theories. But Gordon says, the less fundamental theories only make a heuristic and eliminable contribution to our understanding. Okay. So that's what Gordon says. Now, I'll just quickly remark, I've talked with Gordon about these issues since, and he actually claims he did not mean them as strongly as they read, and that he actually entertains a point of view much closer to what I'm going to defend here. However, ignoring that, almost everybody read Gordon as defending a position that lots and lots of philosophers of science and metaphysicians wish to adopt, that they are only interested in the fundamental part of a theory and not in the grubby tactics used to extract concrete conclusions from them, approximations. And you find passages like this. As a philosopher, I'm only interested in the ontological objects to which a theory is fundamentally committed. How that theory's employers manage to extract practical consequences from these basic tenets will not contribute to this interpretive task at all. And this allows such philosophers to let lots of very complicated issues pass them by. That's a mere approximation. Tain't my style, says Casey at the bat. And this is an unsustainable attitude, I think, and it encourages not looking into the structure of a body of doctrine with sufficient detail to actually understand the tensions that drive that the problems of that field. And that's what, at least nominally, Gordon looks like he's defending this Casey at the bat attitude against Bob. Okay, so let's just start. And at some points we'll get into kind of, this area is very complicated and I don't understand everything that goes on myself. So this is very much a work in process. But let's just start with some things that Gordon says that are misleading in this context. So this is a quote. Suppose that a point source emits light, which then encounters a number of lenses and mirrors. So we've got a telescope and lights coming in. A solution to the wave equation that represents such a process may have a very complicated form. Now, the phrase I want to highlight is solution to the wave equation. There actually is not a single wave equation involved here. If in the simplest case of light coming from a vacuum, entering a piece of glass and then exiting, right, we have different equations that govern this progression and govern the light inside the medium. It slows down and then exits. Okay, so we don't have a single equation here, and you can't make sense of an optical situation if you don't have this sort of joining together of ingredients. Now, you can get confused because in simple media like glass, the wave equation, or the equation that governs how light travels through the medium, is governed by an equation that looks like Maxwell's equations for a vacuum, but with a slightly different term. And that term is sensitive to the frequency of the light inside the medium. Okay. Now, there's a whole progression of complications involved with these extra equations. So if you move to calcite or Iceland spar or sulfur, when the light enters these mediums, it splits in funny sorts of ways. And you need matrix coefficients in your equations to govern the behaviors of these kinds of materials. Okay, so in short, the basic thing I want to alert you to is the story of how light passes through a sequence of various mediums does rely upon postulates about what happens to the frequency of the component light within the beam. This is why frequency is the notion that ties together these different models that we entertain vis-a-vis light, right? So we have to look at how a number of solutions in a series of different equations need to fit together. And by the way, these other equations are notoriously hard to justify, but I won't talk about that. And one gets into worse dilemmas of this nature, which are tackled in the mathematical work that starts in the 1950s at the Courant Institute in New York and in Sweden, that when you have a medium that varies continuously in terms of its refractive index from spot to spot, and a classic case of that is just hot air over a hot desert, where you get a continually changing index of refraction that causes the light to curve, which is why you see mirages. Okay. Now, there's another problem that's closely connected with this that does not involve different equations, but involves situations like this where you have light in a vacuum hitting a screen and coming out the other side. And as well known, you get an interference pattern on a screen when that happens. Now, we have the same vacuum equation governing the light on each side of the screen, but they're subjected to a different spectral decomposition. In other words, we break the light or model the light on this side of the screen as a plane wave, and here as a so-called spheroid, like a circular waves, right? And then there's a question of how to fit these two decompositions together. And that's another example of why we're piecing together, need to glue together different pieces to handle a standard optical situation. And they're general, well, let's not worry about this. I'm making some mathematical mumbling about Fourier integrals, which are very crucial when you look at the detailed mathematics that I'm going to allude to later. Okay. Now, besides these problems I've just discussed, there are further complications, say in that slit problem, about so-called edge diffraction effects that occur at the edge of those apertures. And I'll come back to this edge diffraction aspects of light a little bit later. Okay, at any rate, so these are the complications that should make us go slower about talking about the wave equation in any kind of optical situation. There's always a fitting together of pieces, and the fitting together generally relies upon our ability to break complicated light patterns into arrays of simple single frequency monochromatic light. Okay. Now, the story I'm going to tell is that there's this long history, or I just can do just a bit of it, of changing opinions about where the notion of frequency fits into these piecing together patterns, right? And as these changes have occurred, there have been major changes in how people view the mathematics of what they're talking about. So that's why, back to Worrell briefly, when he talks about the same equation, we're talking about formulas that look kind of the same, but their mathematical understanding in terms of deltas and epsilons and all that turn almost upside down. And this is at least the story I want to hint at today. And my central criticism of Gordon lies in the discussion in the paper, is he doesn't pay any attention to these adjustments, right? He acts as if we're dealing with a set of equations that keep their meaning unchanged, and hence what is fundamental to those equations and what is approximate remains the same. But in fact, these changes in meaning of the equations flip what was originally thought to be a fundamental notion, namely frequency, and convert it to something that has much more the status of being approximate, that's the basic moral I'm after, whether you follow all the details. Okay. Now, there's another second aspect to that same little remark that I selected from Gordon's paper about a point source emits light and then encounters a number of lenses. It's that first sentence that causes the problem, because this kind of phrasing suggests that the optical modelings he's thinking of employ an explanatory scheme or architecture, I call it, that mathematicians call an initial value problem, in which you track the evolving history of a material forward in time. So, and we certainly do model waves that way, and this is an important part of the story. So if we take a piano wire and we hit it with a hammer at a particular point in time, then from that point, which will be characterized by initial conditions of the location of the hammer blow and its strength, right? Then two wave fronts will spread out along the wire, and you see them, you can see pictures of these fronts traveling down the wire. And these are the edge of the wave that goes in both directions down the wire. These lines are called bicharacteristics officially, but they correspond to what Bob calls rays. Okay. Now there will also sometimes be disturbances occurring inside this interval. Okay, but we'll come back to that. Okay, I'll also call these things, this is a standard name, these edges that move along the piano wire are often called pulses, right? And they can be tracked forward in time. So this is an initial value problem where you track how pulses move forward in time from initial conditions, right? And but when you bring frequency on the scene, you depart from that format. And this is a crucial structural feature we need to understand to get the rough idea of what's going on in this talk. When you introduce the notion of frequency, you're thinking of a simple wave, sine wave, entering your wire, say at this point, and then traveling onward from there. And it might split, as happens here. Okay. That notion of having a frequency cannot be reduced to a property of your medium at a single moment in time, like a hammer blow. It actually means that streaming into our situation is a pattern that stretches theoretically infinitely far back away from the medium and temporally infinitely far back. And that is not an initial condition, and was complained about by people like Rayleigh, who actually had a very good understanding of almost everything I'm going to talk about today, though it's often ignored. Okay. What's actually going on mathematically is that we are switching the format of how we're looking at the equations, or looking at our modeling, and moving to what I call a different architecture, which is not initial conditions format. And okay, and let me explain how it works. Here I'm dealing with this, suppose we have water flowing around a block as an obstacle, right? Well, to quote Heraclitus, fresh waters will be ever flowing upon one. So if we track a parcel of water as it passes by this block, we'll be able to actually track it forward in time like this. And this is a manifold, to talk mathematically, that extends forward and has a time dimension to it. Okay, and if you track through that, you can find these particles really following basically these same rays I was talking about earlier as they get around the block. Okay. But we don't want to study those sorts of things. They're very complicated because if the water is at least regular enough, what will actually happen is if you take a flashlight and project down through these layers, you'll get a steady state pattern of the streamlines going around the block, right? This is called a base manifold picture, and it really represents a collapse of all these layers down to a kind of representational manifold that doesn't pay attention anymore to these light waves, but sort of pays attention to the structural patterns that they leave permanently, or that they permanently inscribe. Okay. Lots of physics shifts from starting out like this and almost immediately going over to this kind of setting. Okay, and that happens like on page 1 or 2 of your average optics book. Okay, these figures that we've already cited involving the gluing together of ingredients, right, are these have to be regarded as the base manifold portraits of a steady state pattern in the light. We're no longer trying to track how the pulses of light move forward in time. We're looking at the sort of permanent traces they leave behind if they're moving collectively in a steady state pattern. Okay, if you get some sense of what's going on in the mathematics, which is what's guided me, they classify this as a pure boundary value problem. It's not an initial condition problem anymore. And this distinction, I wish that philosophers would pay more attention to. And in fact, in that book that Edouard mentioned, I go through a lot of Baldirol about simpler cases of what I'm talking about now. And really, if you don't pay attention to these sorts of adjustments, you can get horribly mixed up about very basic issues about causation and so forth, which is what I talk about in the book. Okay. In any case, once you realize that this is the case, you also realize that you can't deal with light in all circumstances in that steady state way. Sometimes you have to bring the notion of pulse back into the picture and have to tell some sort of story that these steady state situations where frequency finds its home sort of represent patterns of pulses that remain organized enough that you can move from this kind of situation to this kind of situation. Now, you don't particularly do too much of that in actually dealing with optics because these pulses are so fast and brief, they're hard. You don't really see them in natural situations. You usually see light, where there's the most common features of light you observe in steady state situations. Okay, now here's where we get the mathematical changes that I wanted to highlight that change our basic conception of what's fundamental in optics and what isn't. To make sense of these waves and their most important features, we have to change the notion of solution to a wave equation, or in this case, to a bunch of wave equations. And theoretically, if you look at an equation, a differential equation naively, it's got to be very smooth. So if you have a pulse of light, it's got to have derivatives everywhere. Okay. Now, what happens in optical situations, and there's a long historical progression, you actually need to allow your solutions to have singularities where those derivatives that are in the equation stop making straightforward sense. So you can put you want to put a sharp front end on your pulses to study them properly. And in fact, you often want to drop off all of the smooth part and just look at how that front singular face, how it moves through your optical situation. And then finally, and I don't know how much of this I'm going to be able to get through, in the very most recent work that I mumbled about, there's something called a wavefront set. It is a peculiar form of singular pulse that is kind of complicated to define. And that's where, but this is now the notion of solution of central interest in the study of equations like this, particularly in light. Okay. And it's in this sort of setting that some of what Bob wants to talk about as important is tacitly involving this sort of super generalized odd notion of solution, right? And of course, it's involved with what Gordon says, but Gordon acts as if we're still dealing with a notion of solution that's pertinent over here. It doesn't pay attention to the redefinitions that start tolerating these things as a form of solution. Okay, now, probably this slide conveys the main things that were buried in my opening moral. And what I say hereafter will just be trying to fill this out a bit. Okay. But it's in this mathematical change I'm talking about that we see this recalibration of fundamental and approximate that I was sort of talking about. So beginning optics books, when you look at them, they actually almost always discuss how light transverses different mediums, the optical situations we're talking about, only in a steady state setting, or what I call the base manifold is projected setting. Okay. As we've seen, that's a very special case of light. It can't be the whole story of light. And so more refined considerations have made people pay more attention to, well, how do these pulses behave? And how do they change when you go from one medium to another? Okay. From this point of view, that notion of frequency, which makes fine sense in a base manifold sort of setting, once you view it, well, that's just a projection from some steady state behavior, and it doesn't take many arguments, and we'll give a few of them along the way, to establish light really can't behave in a true steady state manner. That's only an approximation. So the notion of frequency as we use it in optics has to have the status of being a steady state approximation to a more complicated behavior that's based on the way the light pulses are moving through the situation. Okay, and this is my basic moral that I was after, that the notion of what's fundamental, what's a fundamental quality, or even what's a fundamental solution to an optical problem has almost turned upside down. Okay. And with respect to Gordon's criticism of Bob, just to put it in short order, these redefinitions make the structures that Bob emphasizes and that modern work in optics emphasizes have a much more central place vis-a-vis those pulses, right, than Gordon allows. And Gordon has made the mistake of focusing on this less fundamental situation, namely the steady state kinds of circumstances. Okay, and in this, if you read in optic books, you find sometimes they're kind of funny confessions that this is so. So you can read 300 pages into an optic book and then suddenly come across declarations like this from one of the great masters of modern optics, Emil Wolf. The monochromatic sources and monochromatic fields discussed in most optics textbooks are not encountered in real life. And there's a lot of depth behind what he's saying there. And I think it's kind of funny if you look in a really good book like Booker's Modern Classical Optics, you find these funny apologies. I won't quote it all here, but it takes the form. Well, I tried not to lie to you in the 300 pages before, but I've got to change what I've said. Okay. And these assertions are very startling to a student, right? These reversals. In fact, there's an old song, I'm interested in, folk song, called The World Turned Upside Down. And semantically, that's what happens in the study of optics, right? And a lot of it is involved as a phenomenon I call semantic mimicry in some of my other publications. And, well, let's skip on. Couldn't find, anyway. You can, this is back to the criticism of John Worrell. You can have a situation where it looks like you have the same equation, right? But its meaning has changed so much because of these recalibrations of what a derivative is and so forth that I'm alluding to, that the status of what's a fundamental solution and what is not will completely turn upside down. But because the equations look the same, you'll find people mistaking a steady state solution for a true pulse-like solution and not distinguishing them. And that causes horrible confusions, right? So because, well, anyway, there's a lot of this mimicry involved in those progressions I'm talking about, okay? And the phenomena that you get vis-a-vis what Batterman's being criticized for by Gordon, we might call it Cinderella rescued from the ashes. You know, in the old story, the ugly sisters are supposed to be the noble ones, and Cinderella is relegated to cleaning out the chimney. Okay. These are the fundamental solutions that the philosophers want to study. These are the approximations that we can safely ignore and not invite to our parties. Okay. Under these changes I'm talking about, Cinderella becomes the privileged party, and the sisters, namely frequency, are relegated to the non-fundamental. Okay, now I'll say how much time I have to mumble about this. These sorts of recalibrations, right, or ennoblements, the basic ones that take you to the singular pulse, they have a long history in mathematics, but these tendencies became very pronounced by Lorentz's theory of distributions, which he published around 1950. And almost all subsequent work on differential equations uses these distributions, and they redefine all your operators in your old equations so that these singular pulses become the main solutions. In fact, they're called the fundamental solutions. Okay. So that's, well, actually in that physics avoidance, I talk a fair amount about how the motivation for making these Laurent-Schwartz types changes. The further set of changes are even more radical to take you to a wavefront set. Again, they represent a semantic mimic. They're set up as if you're dealing with the same equations, but you change the meaning and emphasis of how you study those so-called equations so radically that it takes us into quite a different sort of ontological realm, as you were. This is the realm in which Bob's work is mainly concerned, but explaining it is kind of tricky. Okay, so at any rate, to give you a rough idea of what goes on, let's go back to a true initial conditions problem where you have these pulses that travel through a medium, and we're particularly interested in the edges of those pulses, which are called bicharacteristic curves. Now, actually, most of you folks are familiar with those bicharacteristic curves from relativity, because that's the light, so-called light cone, represents the characteristic curves that Maxwell's vacuum equations carve out. Okay. And what we're interested in defining these light cones, there can be light inside, is what goes on at those leading edges. And that's where what you have to look to figure out what the light's velocity is and all sorts of things like that. Okay. Now, light cones are pretty simple objects, but every evolutionary differential equation defines similar cones, though they'll be much more corrugated than those we're looking at here. But when you look at other optical situations of the sort we need to worry about, like calcite and sulfur, those beam splitting things we talked about before, you start getting asked questions you don't have to deal with light in a vacuum, namely, when do those edges split in some way? So a beam of light entering calcite splits into two beams, right? You want to study that in terms of how those edge singularities propagate. They call this the propagation of singularities. Now, the peculiar thing that I just can kind of hint at today is the modern work that involves these wavefront sets decides these are actually the only structures of primary importance that we want to worry about. And this field of study has a name called microlocal microlocal analysis. And it redefines the basic notions of solution in such a way that it only pays attention to these edge singularities. And that's where Bob's rays come in the new situation. Okay, and it is very typical in modern books to reject the idea that rays or wavefronts are approximations. So this is from a very good recent book about these topics, and it says wavefronts and rays are not approximations, nor are they introduced in the manner of traditional geometrical optics. They represent the direct fundamental properties of these edge singularities. Now, it's important to recognize that by paying attention to these details, that's not the full story of what light does. And so these same authors say, there's also what happens to the light behind these singularities, and that requires different sorts of tools. And I'll try to hint at some of those tools. Okay. But to get a sense of what that means, it has to do with those edge diffraction effects. Or if you actually look at sulfur, you don't get pure cones passing through it, but you get light in between the cones, right? And this is the sort of, this in-between light, it's important, but we're going to, micro-local analysis sets it aside and doesn't pay much attention to it. Okay, let me say some very rough things to help orient you towards the way the discussion appears mainly in Bob's book. Is another complication vis-a-vis rays, traditional rays, or even these bicharacteristic curves occur if you just allow light to refocus, because you generate so-called caustic surfaces. And that's where these rays coming in get reflected off such that they start crossing one another. And these, empirically, are the most observable aspects of light, because light gets very bright in these regions where, if we pay attention to rays, we got different rays sitting on top of each other, telling you that light has different intensities. Okay, so just following old-fashioned rays, we actually get something like a contradiction, or the whole apparatus breaks down when we have a situation where caustics form. Okay. And this is the dilemma that Bob wants to deal with. And here's where I can't really go into detail except to hint at it, but it's interesting. What you need to do to resolve this thing is change your notion of a wavefront or array to a more complicated weirdo gizmo called a wavefront set. And it does not possess a notion of frequency, but it possesses a notion of local phase in combination with the notion of a spatial location. An old-fashioned ray or wavefront, its main property was just where it was located. Well, we're going to add an extra property to it and subtract some of that localization. And these are old ideas that actually go back to Hamilton, but they're connected with quantum theory quite intimately, and you'll find a lot of discussion of this connection in the modern optical literature. As you may know, in quantum mechanics, there's a complementarity between properties. If you describe an electron, say, and precisely fix its frequency, you lose all information about where it is, right? If you instead decompose the wave function into location terms so that you can say the particle's here right now, you have no idea of what momentum it has and hence where it's going to be soon. Okay. Where is it? I seem to have eliminated, there it is. What quantum mechanics typically does is, in these situations, say you want to explain what is that seeming trajectory that a particle follows when it goes through a cloud chamber. It's not a true, perfectly defined trajectory. It represents sort of a mixed combination of being partially in a position state and partially in a frequency state. And so its actual state that defines this notion of an approximate trajectory is how you actually want to describe the changing condition of that seemingly moving electron. This is what we need to do with light too in the modern setting, and that's what your wavefront set tries to do. Okay, I won't go into it, but there's a lot of this semantic mimicry going on in that in introducing these redefinitions, they use what are called Fourier integrals that look like they're old-fashioned Fourier integrals, but they're not. And they actually don't make any sense if construed in that vein. They're actually constructions that are redefined so they have the net effect of sort of being like conventional Fourier integrals. Okay, so they're semantic mimics, okay. But they're really not. And this is the crucial thing that you have to pay attention to in this transition to modern rays and wavefronts. Okay, so we really deal with a fill-in mimic that replaces the old-fashioned solution when they break down in the case of caustics. Okay, and it's like these snakes. These are poisonous snakes, and that is a corn snake mimic. Okay. Well, I don't know. So again, this is what my main message, that there's a lot of the world turned upside down recalibration going on in this transition to studying waves in a modern, right waves in a modern form. And there was an old creepy show way back in the 50s called Queen for a Day, where there's this poor downtrodden housewife who for one day got treated like a queen. Okay, very creepy show. But this is what's happened to wave fronts and rays, except it's not queen for a day, it's now queen for the future. Okay, so quickly to finish up, Gordon makes a claim that I find highly misleading that takes the form, I won't quote it, that everything Bob says are merely approximations, and an expert in differential equations would have used those approximations in any case that he or she confronts, right? But they're just approximations, right? What the story I'm trying to say is that this is misleading in many ways. And if you pay attention to these redefinitions that I am dealing with, these changes in foundational recasting have restored the intuitive force that Gordon claims was sapped out of Natterman's discussion, right? So I think that the situation in terms of fundamental is exactly the reverse of what Gordon says. Okay. Anyway, there's a whole another story that makes frequencies look even worse. And that's because real light actually has no derivatives anywhere, right? And that's because it's short bursts of quantum emission. Okay, and to deal with this in your modern books, you have to deal with it as a statistical correlation. So rather than talking about straightforward frequencies and waves, you have to talk about so-called statistical autocorrelations. And these only make sense if you have a relatively stable statistical ensemble. And in that context, again, the notion of frequency has elevated itself. So it's not fundamental, but it's only a property that shows up in these statistical ensemble approximations to what's actually going on underneath. Okay. And so in modern studies, and I'll stop here, they actually, the way they proceed is that they first work on the rays and wave fronts as the fundamental things about light. Those are true of pulses. And insofar as you bring frequency into the picture, as you have to handle lots of phenomena, you drape sort of artificially that statistical flesh over that ray skeleton. And the Russian scientists have a gruesome metaphor. They call this draping wave optics flesh on a ray optics skeleton. But it has a quite interesting meaning in terms of the actual procedures mathematically that they're following. Okay, at any rate, my moral is that because of these changes, and I know I've gone through it very rapidly, there's been this steady progression of fundamental approximative reversal, so that the notion of wavefront refurbished and ray refurbished have sort of become like like Cinderella. They're the ones that are invited to the ball, and the ugly sisters are thrown back into the chimney, the ash pit of approximative. Okay. So anyway, we have to be very careful about, well, this is my moral, no theory is an island. You have to pay attention to these potential changes that occur when as you recalibrate how parts fit together in a complicated situation. Okay, thank you.
All right, thank you, Mark. Let me remind you how we're going to be proceeding. If you have a question, please click on the Q&A button on the Q&A option at the bottom of your screen and write your name, and I will be promoting you to attendee just now. Give me a minute. All right. David, the floor is yours.
Thank you. Mark, I'm extremely sympathetic with all of this, but just for the sake of it, let me try playing devil's advocate and give the line in defense of the analytic ontologist you cited earlier. And if I was going to have to make that defense, I'd probably try saying something like this. These fascinating cases of partial descriptions of transitions, of ways in which various things break down, are the kind of thing you'd expect if we're studying a theory like classical optics, which is partial in its domain of applicability, both spatially partial because it doesn't itself pretend to be a theory of media, it just takes media as input, and also partial in the sense that it gives way to quantum mechanical phenomena on appropriately short length scales, and so the theory has to be finessed in a bunch of different ways to handle those various domain restrictions. But I, the analytic metaphysician, am interested in fundamental theories.